Okay, so we can start with the second part of today's talks. And the first speaker of this part is Sebastian Velázquez from Universidad de Buenos Aires, who will give a talk about Moduli spaces of Lie algebras and foliations. Thank you, Sebastian.
Thank you, Paola. Hi, everyone. First of all, I want to thank the organizers for giving me the opportunity to give this talk. And as you can see by the title, today I'm going to work about work in progress, about the interaction between Moduli spaces of Lie algebras and Moduli spaces of foliations. So along this talk, X will denote a smooth complex projective variety, and the aim today is to address the problem of understanding the geometry of Moduli spaces of foliations on X. Okay, so this problem is a very active area, and primarily in the case of projective spaces, and not much is known for other varieties. So we'll make our attempt. And since this is a short talk, I will try to keep the technicalities to a minimum. So let us start with basic definitions. So we'll work with involutive distributions. A single involutive distribution F of dimension Q and X is a short exact sequence like this.
Sorry, Sebastian, we can still see the title, at least me. It's not changing.
Me too.
Mm-hmm. Okay. That's now?
Yes, I mean, now you're seeing involutive distributions.
Nice.
Yes.
Don't know what happened. Thank you. So a single involutive distribution of dimension Q and X is a short exact sequence like this, where the rightmost term, which is called a normal sheaf, has rank Q, and this here is an inclusion of a coherent subsheaf of the tangent sheaf, which is closed under the Lie bracket of vector fields. The singular scheme of such an object is the singular scheme of its normal sheaf, which is the points where it fails to be locally free. So before we talked about foliations, so what is the relation between this and singular foliations on X? Well, outside its singular scheme, such an object induces a foliation, a regular foliation. There's a picture. So by Frobenius theorem, this induces the composition of the complement of the singular scheme into connected holomorphics of varieties, such that locally around each point X, we have an holomorphic chart trivializing this composition like this. So these components here, the blue ones, are called the leaps of the foliation or the distribution, and are usually not algebraic. Okay, so a few examples of this. If we have a smooth map, we can look at the exact sequence defined by its differential. Here, the relative tangent sheaf with respect to the map is automatically involutive because it is the kernel of a map of Lie algebras. The leaves of the induced foliation would correspond to the fibers of the map. And similarly, if we have a dominant rational map, it also induces a foliation in X. And then there's the family of examples that we are particularly interested in today, which are foliations induced by global Lie group actions. So if we have such an action, this is a morphism from G, from some Lie group G to the automorphism group of X. We can look at the derivative at the identity. This is a map from this Lie algebra G to the algebra of global vector fields in X. And so tensorizing this by the structure sheaf, we get a map from the trivial sheaf with fiber G to the tangent sheaf of X. And we define the associated distribution to be the one that has tangent shift equal to the image of this morphism. Again, this is automatically involutive because it's the image this time from above Lie algebras. And the orbits of this foliation correspond to the leaves of the foliations correspond to the orbits of maximal dimension. So now I will try to convince you that these foliations distributions are quite particular. Well, of course, they satisfy that this tangent shift is globally generated, but also their leaves have some extra structure. First, a definition, a symmetry for a foliation is an element X such that it is not tangent to the foliation and such that the associated exponential map leaves the distribution or the foliation invariant. It maps leaves of f into leaves of f, but not the same leaf because otherwise it would be tangent to the foliation. And in order to give this object a structure of vector space, we have to look at the global vector fields satisfying this condition here, leaving the foliation invariant modulo the ones that are tangent to the foliation. So what is particular about these foliations that I wanted to tell you is that is this theorem here, which I believe is due to Cervon de Certi, and which says that if we have such a foliation, such an evolutive distribution, then either it admits a symmetry or every leaf of f is algebraic, which is, to me, highly non-trivial and particular because general foliations that do not satisfy this. Well, I have to say that maybe I'm confusing the term foliation and evolutive distribution because I forgot to say that we saw that every evolutive distribution defines a foliation, but also every foliation is induced by an evolutive distribution as we defined, and the correspondence is bijective if we restrict ourselves to the case where the normal shift is torsion free. So maybe that's why I'm unconsciously confusing those words. Okay, so now I can tell you the motivation of this work. It's about a work of Professors Kuckerman and Pereira. In this work, they study, among other things, foliations in projective spaces that are induced by locally free Lie group actions. They prove that under some hypothesis on a foliation, on an action, the map that sends a subalgebra of the Lie algebra of global vector fields into the associated foliations, such as we constructed before, is a local isomorphism. Okay, so maybe I would say a quick guideline of the ideas there. This is the following. So if we have such an if the tangent shift of a distribution, evolutive distribution, is trivial, then it must be associated to some subalgebra of the global vector fields on X, with the action having trivial stabilizers in dimension 1. That's what I mean with when I say locally trivial, okay, locally free. And also it holds that if we have another foliation sufficiently close to the original one, then their tangent shifts are isomorphic. So there must be another subalgebra close to the original one, such that it is the associated foliation to this new subalgebra. And in particular, if we begin with a subalgebra admitting only trivial deformations as a subalgebra, then we will end up with a rigid foliation. Okay, and this is nice because it tells us how the reducible component where this foliation stands looks like. So the natural question now is the following: what happens if the stabilizers are not trivial, or if X is a more general variety? And we will see that the picture is the same as long as we are standing at the foliation, such that its tangent sheaf as trivial first chronology group. Okay, so now let's give more precision about these moduli spaces and its interaction. So a family of singular inequality distributions of dimension Q with base S is just the relative version of what we said for single distributions. Here, that this here is the relative tangent sheaf of x times S with respect to the projection to S. And the family is called flat if its normal sheaf is flat over S. So now that we have the definition of family, we can define the functor of families of distribution, which assigns to each scheme S the set of flat families of integral distribution. And if we fix a polynomial P, we can also require that the normal sheaf has Hilbert polynomial P in each fiber over S. So we just defined a subfunctor of the corresponding quad scheme of the tangent sheaf of X. So it would be reasonable that this functor would be represented by a subfunctor, and this is true by a theorem of Quadrum, sorry, by a subscheme of the quad scheme. So this functor here is represented by a closed subscheme of the corresponding quad scheme, and we will just drop the subscript indicating the polynomial and just work with the disjoint union of the schemes. And just a quick reminder and observation is since the automorphism group of X acts on the quad scheme and sends involutive distributions in involutive distributions, so it also acts on our moduli space by change of coordinates. We will say that an element is rigid if its orbit by the automorphism group of X contains a non-empty space key open. So now for every foliation F, we can define the following complex of sheaves, which looks like a Chevalier-Eilenberg complex for the tangent and the normal sheaf. So this here, the differential is defined here, and the hat over this element means that we're taking the wedge product over each element, over every element except the ones indicated in the subscript. If we restrict, this complex is called the leaf complex, because if we restrict it to the non-singular points of X, we end up, except of the first time maybe, we end up with the sheaf of differentials along the leaves with values in the normal one. So we can use this complex in order to understand our moduli space locally. So recall that we have our moduli space is a closed subscheme of the quad scheme, and we know from the literature that the tangent space to a point F to the quad scheme is isomorphic to the maps, the space of maps between the tangent sheaf and the normal sheaf. So we'll keep track of this isomorphism here. And well, I will not explain the whole diagram, but we can construct a diagram explaining exactly how we can use this isomorphism and the leaf complex in order to understand the tangent space to our moduli space and to the corresponding orbit. Okay. Now let's return to the moduli spaces of subalgebras. So for every scheme over C, we can define what is a family of Lie algebras, which is a locally free sheaf together with a bilinear morphism satisfying the Jacobi identity at the level of local sections. An example, a trivial example, would be the following. Just take any Lie algebra and look at the trivial sheaf with fiber this Lie algebra, say L. and you can extend its Lie bracket linearly. So in the language of deformation theory, this would correspond to abstract deformations. And we will not work with abstract deformations. We will work with embedded deformations. So this will be our trivial abstract deformation of L. And the idea that corresponds to embedded deformations is the following. If we have, again, a Lie algebra L, a family of subalgebras of L over some base S is a locally free subalgebra of the trivial deformation of L over S, such that it is closed under the Lie bracket we just defined. So we can define the functor of subalgebras of L of dimension D, assigning each scheme the set of families of subalgebras over such scheme. And just as in the, first an example, we can take S to be automorphism group of X and G some subalgebra of its Lie algebra, which is the algebra of all vector fields. And well, we know that the automorphism group acts on its Lie algebra by its adjoint map. And we can construct, like it says here, the family of subalgebras over S such that over each point X, we have the subalgebra, which is the image of our original subalgebra G by the adjoint map corresponding to that point X. Okay, so just as in the case of involutive distributions, this functor is represented by a closed subscheme of the Grassmannian. And well, from now on, we will work only in the case where L is what we just said, the algebra of global vector fields on X. So we will drop the notation for L. And a quick reminder again is that the automorphism group of X acts on this, again, on this moduli space SD by change of coordinates. Actually, the action of the automorphism group of X at a specific point corresponds to the family here we just defined at the bottom here. And we will say that an element is rigid if its orbit contains, again, a non-empty Zariski open. So since this scheme represents our functor, it comes with a universal family like this. And we can use it to generate a family of involutive distributions on X like this. So as we did for a single subalgebra or for a single Lie group, we can tensor this here by the structure sheaf. And if we think of L, so L is the global vector fields on X, as if we think of L as a global vectors on the fibers of the projection, we can we get a map from, again, this sheaf here to the relative tangent sheaf, and we define the family of distributions to be the one that has tangent sheaf equal to the image of this morphism. Again, exactly the same as we did with a single subalgebra. So what we get is a family of distributions such that over each subalgebra, we have the foliation or the involutive distribution associated to the action of the subalgebra. So we have to have a little caution, because this family shouldn't in general be flat, because, for instance, the codimension of the family can jump. And since we want to compare moduli spaces, we will need flat families of distributions with base over some space of subalgebras. So what we have to do is we have to take a flattening stratification associated to the normal sheaf, so that now when we restrict to each of these strata, we get a flat family of inequality distributions. And so, since our model space of foliations or inequality distributions also represents its functor, then these flat families would correspond to a morphism like this from each strata to the model space of inequality distributions, and such that the restriction of our family is a pullback of the universal family here. Okay, so recall in the motivation, we asked what happens if the stabilizers were not free, or if the if X was a more general variety. So now that we have said everything we have said, we can convince ourselves that the only question that actually makes sense is to ask which are the conditions such that this morphism right here is a local isomorphism. So our answer today will be the following theorem. If we happen to be standing at a point such that the Lie algebra is exactly the space of global sections of the tangent sheaf of its associated foliation, a priori this should be an inclusion. And also, said this tangent sheaf has first cohomology group 0, then what we have said holds. This is a local isomorphism around this point. And also, it sends the orbit by the automorphism group into the orbit of the automorphism group on the other side. So if we are standing at a rigid subalgebra, then we end up with a rigid foliation. So with corollary, since Lie subalgebras are known to be rigid, if we're standing as a Lie subalgebra satisfying these two hypotheses, then the corresponding foliation will be rigid. And so now the natural question is, okay, so when do these hypotheses hold? Well, of course, if we have an action with trivial stabilizers in dimension 1, just as in the work of Huckermann and Pereira, and we require the structure sheaf to have first cohomology 0, then this morphism right here that we knew that it was only an epimorphism will be an isomorphism, and therefore the hypothesis will hold. And okay, so what if the stabilizers are not trivial, the action is not locally free? Then again, this will be an epimorphism, but it will not be an isomorphism because we will have syzygies. So we will require, if we require the last syzygies to be 0, then our hypothesis will still hold. What I mean by this is that if this morphism admits a resolution like this in PM, sorry, I forgot to say that now we're in PM, then our hypothesis will hold. You can just make the calculations. And an example of the example would be the adjoint representation of the special linear group. And so this representation, there's a definition, and the deeps correspond, as we said, to the orbits of maximal dimension. The general orbit actually corresponds to the fiber of the characteristic polynomial. And this morphism right here admits a resolution like this, one-step resolution. So this is a rigid involutive distribution. Okay, thank you. That was all.
Thank you, Sebastian. Thank you. There is some time for questions or comments, if anyone has. Okay, so if not, let's thanks Sebastian again. Thank you very much for the talk.